Hello, ladies and gentlemen. It's my great honor to have a brief introduction of our recent work. And our topic today is multiparameter optical performance monitoring using eye diagram measurement and convolutional neural network. And our report is divided into the following 5 parts. And before getting into the theme, I will introduce some background relative to our work together. First, let's overview some information about optical communication system. And today's optical network function is a fairly static fashion is built to operate within well-defined specifications. And this process is quite challenging for higher capacity systems since network patterns are not static. And network effect can change the temperature, component drift, impairments, such as power loss, noise, chromatic dispersion, polarization, mode dispersion between receiver, transmitter, fiber, amplifier, and so on. On the other hand, elastic optical networks are flexible to divide the network source adaptively to maximize the bandwidth and energy efficiencies. In elastic optical networks, transmission parameters like modulation format, bitrate, signal power, transmission path, spectrum assignments can be adjusted. The dynamic variation of transmission parameters in elastic optical networks imposes new requirements on parameters monitoring technique, and it is potential for enabling higher stability and flexibility in an optical network. And the management of available resources in complex networks will be a challenging task and would require the gain of real-time information about the quality of physical links, as well as optical signals. We need to pass all this information to the network management system possibly for impairment wire routing and fault localization and diagnosis. Consequently, it would be beneficial to implement channel performance monitor to determine their changes and optimize the network accordingly. A series of optical performance monitoring techniques have been proposed in recent years, capable of monitor various link impairments and the quality of optical signals. As for WDM systems, higher capacity is required to economically meeting the increasing demand for communication services. The WDM channel management layer monitoring involves a determination of the optical domain characteristic essential for transport and channel management, such as real-time measurements for channel presence, power levels, and the OSNR. Essentially, an effective monitor should be able to detect the outage for network fault management to the identification, diagnosis, resolution, and tracking of faults in network. In a word, a self-management WDM network can utilize OPM information to optimize the performance or reroute the traffic. And there are 3 layers of OPM in WDM system: transport monitoring, signal quality monitoring, and protocol monitoring. And by capture different medium, such as the amplitude histograms, constellation histograms, and eye diagrams, key information can be. Is one of the basic signal medium in the optical communication systems, which reflects an overall characteristic of digital signals and estimates the signal's quality. Eye diagram images can be collected by low-speed sampling oscilloscope, and this figure shows a mirrored eye diagram at the transmitter, and the same eye after noise have been accumulated. And the effects of dispersion and modulation format of eye diagrams are also shown here. And with the continuous development of artificial intelligence technology, machine learning is widely used in various fields, such as biomedicine, natural language processing, and computer vision. There are some methods like k-means, random forest, and principal components analysis, deep learning. Deep learning as one of most advanced branches of machine learning techniques of data of multiple levels of abstraction and has a and has been developed for many innovative optical applications. And we can see the structure of neural networks, which are combined with neurons and layers. So many works apply the machine learning method into PM. The management will be benefit for real-time monitoring issues. Over the last few years, we have seen several research works focusing on the applications of machine learning algorithms in various aspects of optical communications, such as fiber nonlinearity composition, data centers optimization, intelligent testing and measurement equipment realization, network planning and performance prediction, and so on. And we give out some examples. When trying to send more data further, the challenge in most communication systems is noise, and optical amplifiers are generally used in networks with broad extent to provide gain that reduce the attenuation of the fiber. An inevitable byproduct of optical gain is optical noise propagating along with the signal. The presented results show that techniques from machine learning, such as neural networks-based nonlinear regression and support vector machine classifiers, are beneficial for OSNR estimation. It has been shown experimentally that estimation of in-band OSNR is achievable from directly detected PDM signals, employing advanced modulation formats of up to 64 qm with varying pulse shapes. And the dynamic variation of transmission parameters in elastic optical networks imposes new requirements on both OSNR and format monitoring technique. For example, the OSNR monitoring must be appropriate for the incoming signals with different modulation formats. The real-time information about modulation formats are not only can help OSNR monitor choose the most appropriate algorithms for the estimation, but also can help coherent receiver choose appropriate digital signal processing algorithms for these format types. Consequently, modulation format identification is necessary for OSNR monitor and digital coherent receivers. Recently, several techniques for modulation format identification using coherent detection have been presented. And similarly, thanks to the opportunity to learn the mapping between the adapted format and the feeders of the incoming optical signal. In this paper, a CNN-based constellation diagram analyzer was proposed to implement both modulation format identification and OSNR estimation. 6 widely used modulation formats were comprehensively evaluated. And next, I will introduce some widely used machine learning methods. The first module is decision tree. A decision tree is a flowchart-like structure in which each internal node represents a test on an attribute. It can directly reflect the characteristic of the data very fast and is not susceptible to extreme data, but it is not fit for continuous target variables and easy to overfitting. And another basic classification and regression machine learning method is k-nearest neighbor algorithms. The KNN has 3 fundamental elements, distance measurements, size of k, and classification rules. The KNN model can divide the feeder space into some subspace for the test point to find the subspace to which it belongs. It's suitable for large dataset, especially for multiparameter problems with no training process. However, it is not fit when the samples are unbalanced. A support vector machine is an algorithm to minimize structure risk by constructing the optimal decision surface. It can achieve nonlinear classification by kernel method with lower error rate and avoiding overlearning problems, but it is sensitive to missing data and needs large costs of space and time. By comparison, the CNN-based approach can automatically extract abstract feeders and achieve higher accuracy with potentially less computation resources, aiming at our classification issues. And accordingly, we further use Mobile Night, which is a lightweight module with less parameters and computations. Based on the depth-width spiral convolutions for VGG module, is a kind of CNN. Its convolution core is used on all the input channels, where depth-wise spiral convolution based on Mobile Night is different convolution cores. Depth-wise convolutions and point-wise convolutions for each input channel. By comparing these two methods, the computation reduction of of the Mobile Night over VGG of one specific layer setting is shown as this function. And next, I will introduce our researchers about the multi-parameter monitoring of coherent channel. And this figure illustrates the structure of a point-to-point WDM optical system. In the physical layer, I diagram from a channel under the test can be obtained with a tunable bandpass filter and I diagram measurement. And is then sent to the network cloud, and machine learning can help identify the channel performance drift. Accordingly, the SDN controller send control requests to reconfigure the transponders, thus improving the overall system performance. And this figure depicts the experiment setup to capture eye diagrams of 32 gig baud signals with different OSNR, roll-off factor, modulation format, and IQ skew. The OSNR is adjusted by an ASE source with a variable optical attenuator, while roll-off factor and IQ skew are controlled by a 92 gig samples per second DAC. The coherent DAC receiver with offline DSP processing is also utilized to monitor the signal from the coherent transmitter. A digital communication analyzer is used to capture the eye diagrams from the coherent transmitter, and the images are collected for machine learning processing. And as shown here, we experimentally generated a large set of eye diagram images for 32 gig baud signals with different parameters, including OSNR 15 to 40 dB, and roll-off factor from 0.02 to 1, and IQ skew from -10 to 10 picoseconds, and 3 modulation formats, including QPSK, 8 cram, and 16 cram. The images are grouped into 36 sets according to different combinations of parameters. And we further class these 36 sets into 7 classes by single or multiple parameters. And we use 3 traditional machine learning techniques and methods for the above classification problem. And CNN is typically combined by multiple convolution layers, polling layers, and fully connected layers. And in the proposed technique, we mainly used VGD-based CNN with 4 convolutional layers for parameter prediction. The first CNN has 3 channels with our sample input and input eye diagrams are pre-processed first. And we use different filter for each convolutional layers and set ReLU. And the max pooling layers are used by stride of 2 multiple linear regression and soft max algorithms are typically applied to classification problems. And for different modulation formats, we collected 360 eye diagrams images, which contain the feeders of QPSK, 8 cram, and 16 cram signals. And all methods extract both the local and global feeders of the eye diagrams. Images are divided into training and testing sites by randomly selecting 80% and 20%. And furthermore, we also take the lightweight Mobile Night model into consideration here. And the result shows accuracy of different machine learning methods aiming at the modulation format monitoring. It is a relatively simple mission. And the VGD-based CNN, Mobile Night, and SVM perform better than the others with 100% accuracy. And the amount and complexity of the feeders determine the accuracy of different machine learning algorithms. And when the feeders are complex, the difference in accuracy between CNN and the traditional machine learning method is more pronounced. CNN has higher accuracy due to its deep convolutional structures. Accuracy of these two CNN methods are very close to each other for each classification issue. So in our following accuracy line chart, they are expressed by a single line. And the advantage of CNN is more obvious in OSNR classification over skew with fixed 1 raw factor under 15 dB OSNR and 30 dB OSNR. And the OSNR classification over raw factor with a fixed IQ skew equals to 1 under 15 dB OSNR. We can see that the prediction accuracy for decision tree decreases significantly for high raw factor region, and it has an accuracy of lower than 80% for 1 raw factor, but the CNN-based method has nearly 100% accuracy. And when then increase the complexity of the classification problem by varying two parameters together, for joint raw factor and skew monitoring under different OSNR, the difference of accuracy is more than 20% between CNN and the other methods under 15 dB OSNR. Moreover, these two figures both show the CNN has the highest accuracy, which is close to 100% for all the conditions. It clearly shows that for classification problems, the stability and accuracy of the CNN are better than the ones of the other machine learning methods. And furthermore, we put all the eye diagrams images of different combinations of modulation format, OSNR, raw factor, and skew in a big data set. To monitor coherent channel performance with eye diagram measurements, CNN-based deep learning method performs better more than the other traditional machine learning methods. Two CNN-based methods, one is VGG-based and the other one is MobileNight. They both have high accuracy for the above OPM problems with different complexity, especially under low OSNR region and for IQ skew monitoring issues. We further calculate the computation of some layers in the two CNN networks, which is shown in this table. And in comparison, the computation cost reduction of the 4 convolutional layers using MobileNight are around 30%, 80%, 90%, and 95%, respectively. And in sum, compared with the VGG, MobileNight has present loss while reducing computation and storage space significantly. And next, I will introduce our recent work about multi-parameter monitoring of IMDD channel using PAM signals. And in order to utilize bandwidth resources more efficiently, the WDM system combined with IMDD is widely used in today's data center networks to enlarge the data carrying. Here is the structure of both the intra and inter data center systems based on WDM IMDD with eye diagram monitoring using machine learning. And the monitor nodes are usually implemented at the transmitter side or in front of the receiver. Eye diagrams of one wavelength channel can be collected through a tunable bandpass filter and digital communication analyzer. And the collected images could be uploaded to the network cloud for machine learning to process the data and identify the image characteristic. And the experimental setup is used to capture the eye diagrams of PAM-based IMDD channel with different parameters related to both the digital signal, including baud rate, raw factor, modulation format, and probabilistic shaping, and optical link, including OSNR and chromatic dispersion. Meanwhile, the pre-equalization based on the feed-forward equalization is utilized, and then the pre-distortion is also used to compensate the nonlinearity introduced by the devices. As for the optical link, a flag noise is achieved from the NSE noise source filtered by a bandpass filter, and the noise can be adjusted through a variable optical attenuator to control the OSNR values in the channel. And the different values of chromatic dispersion are realized through a tunable dispersion compensation module to simulate dispersion accumulation in the transmission. And then the eye diagrams are captured by DCA after controlling the received optical power. Totally 6 parameters are selected for joint monitoring, and all collected images are then divided into training and testing sets for classification based on machine learning, including 3 traditional machine learning and 3 modern CNN modules for comparison. And here is some eye diagrams of PAM signals with different parameters. And we can see that the chosen interval of different parameters, 3 parameters contain 4 values and the other 3 contain 3 values. And meanwhile, 10 images are collected for each class so that there is a total of 1,728 classes and 17,280 images as data sites. And due to different network architectures and hyperparameter choice, the performance of CNN will vary greatly. And some modern CNN modules have different layer structures and combinations to achieve higher accuracy while also further reducing the computing resources. And here, a VGG-based module is mainly used, and we also consider the commonly used Resonite 18 and the lightweight mobile night and the recent efficient night V2. And for a typical VGG-based block, it includes a multiple convolutional layers, a batch normalization layer, and a max pooling layer. And here we also designed the VGG-based module with 4 blocks compared to the commonly VGG 11 module. Here we designed to reduce the number of convolutional and max pooling layers by half, achieving a much better trade-off between accuracy and computation costs. And first, all the 6 parameters expected modulation format are divided into 2 sets: digital signal parameters and optical link parameters. Here, these two figures, A and B, show the accuracy of joint monitoring 2 optical link parameters and 3 digital signal parameters, and the different modulation formats and learning methods. It can be clearly seen that the VGG-based CNN and SVM outperforms the other methods, achieving higher accuracy close to 100%. And next, the complexity of the classification is increased to 432 classes for each modulation format, and different combinations of all the digital signal and optical link parameters. And under more complex conditions, the accuracy of SVM decreased to 85% with the increase of PAM order, while the VGG-based CNN can still maintain greater than 96% accuracy for all the conditions, which is much better than the other 3 methods. And finally, when the complexity of the classification is increased to 1,728 classes under different combinations of all the 6 parameters, including modulation formats, the advantages of CNN over traditional machine learning has become more obvious. And here we can see that under the most complex conditions, 97% accuracy is achieved by VGG-based CNN, which is 10% better than the highest accuracy among the other 3 methods. Therefore, thanks to the higher accuracy and the ability to adapt various simple and complex scenarios, CNN represents a better choice for accurate performance monitoring of PAM-based channel. And furthermore, we adopted 4 modern CNN modules, including VGG-based module, Resonite 18 module, Mobile Night V3 module, and Efficient Night V2 module, to achieve joint classification of all the 6 parameters and explore the most cost-efficient method. And the figure on the left shows the accuracy curves of the first 30 epochs of each module. And we can see that the accuracy of all the modules can converge to a stable value within 30 epochs. And the figure B on the right used the box plot to show the accuracy distribution of the last 150 epochs of each CNN module. And basically, all these 4 modules can reach a high accuracy of greater than 96% for jointly monitoring all the 6 parameters of the PAM-based channel. Among them, Efficient Night V2 take the leading role with an accuracy distribution centered on around 97%. And some key parameters reflecting the complexity of the modules are also compared here. And in contrast, MobileNet v3 realized fewer parameters and flops by using mobile bottleneck convolution block. And meanwhile, the VGG-based module design here utilize fewer convolutional layers to achieve the least memory usage. And neither of these two methods comes at the expense of accuracy. And therefore, MobileNet v3 and the designed few-layer VGG-based modules seem to be more cost-efficient for jointly monitoring all the 6 parameters. And I will give a summary of the presentation. And first, we use the I-diagram measurement to monitor multiple system performance parameters of an optical coherent channel using CNN-based techniques. And the proposed CNN approach could potentially achieve classification and monitor of single or multiple parameters of a coherent optical transmitter with higher accuracy and less hardware complexity. And furthermore, traditional machine learning methods greatly rely on complex iterative algorithms and require more computation power or even human intervention. And furthermore, we also propose to utilize I-diagram to monitor multiple performance parameters of an IMDD channel in optical communication system using CNN-based methods. And our designed VGG-based module with fewer convolutional layers could achieve joint monitoring of both digital signal parameters and optical link parameters of the PAM-based IMDD communication system with higher accuracy and less memory usage. And the I-diagram-based deep learning method has relatively low requirements on implemented hardware, and its application can also be extended to monitor chromatic dispersion, polarization mode dispersion, crosstalk, nonlinear distortion, IQ imbalance, and predict network failure. And that's all of my presentation. Thank you very much.